All right, let's dive right in. For this explainer, we're going on an incredible high-speed adventure. We are going to follow one single piece of data on its journey, from your computer across the entire world and back again, all in literally the blink of an eye. So let's trace that path, step by step.
It feels like magic, doesn't it? One second you click, the next, a website from halfway around the world is right there. But it's not magic. It's actually a beautifully choreographed dance between hardware and software. And we're about to pull back the curtain and see exactly how it all works.
So before our little piece of data can even begin its journey, we have to ask a really fundamental question. Why do we connect computers at all? I mean, a computer by itself is a powerful tool, for sure, but it's kind of like an island. To really unlock what it can do, it needs to connect to a network.
And the reasons why, well, they're things you and I do every single day without even thinking about it. We share files, right? Or how about sharing one printer with an entire office instead of everyone needing their own? That's a network. Sharing one internet connection for a whole house? Yep, that's a network too. It just makes everything from security to communication so much easier.
Now, our data is going to travel across two main types of networks on its trip. It starts its life on a LAN, a local area network. Just think of the Wi-Fi in your house or the network at your school. It's local. But to get out into the big, wide world, it has to jump onto a WAN, a wide area network. And the biggest, most famous WAN of all is, of course, the internet.
Okay, so here we go. The journey begins. You've just clicked a link. That click instantly becomes a small chunk of data inside your computer, and its mission is to get out into the world. The very first leg of its trip is just getting across your local network. And to do that, it's got to meet a few key pieces of hardware.
The very first stop is the Network Interface Controller, or NIC for short. You can think of it as the passport control for your computer. It's the part that takes the digital data from your machine and translates it into a signal that can actually travel, either an electrical pulse down a wire or a radio wave for Wi-Fi. It is the literal gateway out.
Okay, passport stamped. Next, our data hits a switch. A switch is like a really smart local traffic cop. It knows exactly which device is plugged into which of its ports. So instead of just shouting the data out to every computer on the local network, it intelligently sends it only to the specific device it needs to go to next. This keeps things running fast and smooth.
But hold on, what if you're on Wi-Fi, like most of us are? Well, there's one extra step. Your data travels as a radio wave to a wireless access point, or a WAP. The WAP acts like a bridge. It catches that wireless signal and turns it into a signal that can travel over a physical cable, where it usually gets passed right along to the switch. Now, this next point is absolutely crucial. A switch manages traffic inside the local network, but our data wants to go to the internet. For that, it needs a router. A router is the main exit, the gateway between your LAN and the giant WAN. Its whole job is to forward data from one network to another, officially sending our packet out on its globe-trotting journey. And it's pretty amazing to think about how this is physically happening. On your local network, that data is probably zipping along as electrical pulses in a standard copper Ethernet cable. But for the long haul, for that journey across the internet's backbone, it gets converted into tiny pulses of light and shot through incredibly fast, hair-thin fiber optic cables that stretch across continents and lie on the ocean floor.
And just like that, our packet has left the building. It's now flying across the wide area network, the internet, navigating a sea of trillions of other packets. But it's not always a smooth ride, you know. There are several things out there that can affect its speed. One of the biggest factors is something called bandwidth, and this analogy is just perfect. Bandwidth isn't really about speed, it's about capacity. Think of it like a highway. A car can go 60 miles an hour on a one-lane road or a 10-lane highway, but the highway can handle way more cars at once. A fiber optic connection is that 10-lane highway. An old dial-up connection, that's the tiny one-lane road.
And there are other things too. How many other people are using the network? That can cause a digital traffic jam. The type of connection matters. A wired connection is generally more stable than wireless. If the signal quality is poor, you get errors, and the data has to be sent all over again. And finally, there's latency, which is just a fancy word for a delay caused by the sheer physical distance the data has to travel.
Now, with all these billions of devices and trillions of packets flying around, how does this system not just collapse into total chaos? The answer is that every single device, from your phone to a massive server, has agreed to speak the same language. They all follow a very strict set of rules, and these rules are called protocols.
And this really is the best way to think about it. If you don't have a common language, communication is impossible. It's that simple.
Protocols are that shared language for every device on the internet. It's what allows a computer in one country to send a packet that a server in another country can understand perfectly.
So let's meet some of the key players. The big one, the absolute foundation of everything, is TCP/IP. It's like the constitution for the internet. Now, for our packet-specific journey to get a website, it's using the HTTP protocol, or more likely HTTPS. The S just means it's secure. In fact, HTTPS is the protocol working right now to bring this to you.
So how does a computer manage all of these different rules at once? Well, it uses a really clever idea called layering. Instead of trying to solve the massive problem of networking all at once, it breaks it down into smaller, manageable jobs. Each layer does its one specific task, adds its own bit of information, and then passes the data down to the next layer. It's like wrapping a package.
So let's see this in action. At the very top, the application layer gets our web request ready using HTTP. Then, the transport layer chops that request into smaller, numbered packets. Next up, the network layer acts like the postal service and slaps on the destination IP address, the global address for the website server. And finally, the link layer adds the address for just the very next hop on the journey, like our router. And there you have it. The packet is fully wrapped and ready for mailing.
Okay, our packet has crossed oceans and continents, hopping between countless routers, and it's almost there. It's about to arrive at its destination computer. But what kind of computer is it? Well, in the world of networking, there are basically two main models for how devices interact.
Since our packet is asking for a website, its destination is a server. A server is not like your desktop PC. It's a high-performance machine, usually living in a massive data center, whose entire job is to serve up data, like web pages, videos, or files, to other computers. And those other computers, like the one you're using right now, are called clients.
So, grabbing a web page is the classic example of the client-server model. It's centralized, it's organized, your client asks, the server provides. The other main model is peer-to-peer, or P2P. In that model, there is no central server. All the computers are equal or peers, and they share files directly with each other. It's great because there's no single point of failure, but it can also be less secure.
And touchdown! Our packet has arrived. The server has received your request. And what does it do now? It starts this entire process all over again, but in reverse. It finds the website data, wraps it up in all the same protocol layers, and sends it on the long journey back through all those routers, all the way to your screen.
So let's just do a quick recap of that whole incredible trip. It all started with a request from your computer, the client. It traveled through your LAN hardware, like the NIC and switch. It left your local network through the router to get on the internet. It was guided by protocols like TCP/IP and HTTP until it reached the server. And then, the whole thing happened in reverse. Every single click, every stream, every message you send follows these exact same steps.
It's truly an incredible system, built over decades that connects billions of us. But we're now in the process of adding billions more devices. Not just computers, but cars, refrigerators, you name it. And that leaves us with a huge question for the future. How do we make sure this global network we all depend on can evolve to handle that and stay fast, open, and secure enough for everyone?